Okay, so we ended class today on this last line. And each class ended in a slightly different place, but we ended up in the part of the proof we're trying to figure out what our choice should be for delta. And we're left with this idea that when we go into the preliminary analysis, or we come to call it the cheating part of the proof, I don't want, okay, so what I'm writing right now is what I don't want to do. I don't want to simply create an expression for a choice. So I don't want to say delta is equal to epsilon over the absolute value of x plus 1. Because that's not a numerical choice. We always want delta to be a specific number choice in the problem. So instead we go back to this product that we have, and I'd like to try to remove one of the two factors. In this case, I'd like to try to remove the x plus 1. I'd like to do something numerical with it, figure out, okay, what other inequality could I possibly write that got the x plus 1 out of the problem while leaving the x minus 1 in the problem. So one of the powerful things about delta is the idea that we get to pick what delta is going to be. And so while in all of these problems we're trying to pick a delta that works for all possible epsilons, sometimes we might just be able to pick a delta that works for some of them and then figure out what the rest of them would need to be. This is what we're going to do here. So we're going to let delta be equal to 1. Okay, so we're going to say, okay, well, delta is going to be equal to 1. And that delta equals to 1 will work for some epsilons. There'll be some epsilons where it works, and there'll be some epsilons where it doesn't. What we can state if delta is equal to 1 is that the absolute value of x minus 1 is less than delta, which is less than or equal to 1. Right? Which tells us that x minus 1 is less than 1. Okay. So this doesn't really help us necessarily get rid of x minus 1 over here until we think about trying to get x plus 1 as something we know more information about. What we'd really like to know is something about x plus 1. So when I rewrite that absolute value as negative 1 is less than x minus 1, which is less than 1, I'm really thinking about introducing x plus 1, right? The absolute value of x plus 1, or just x plus 1 in general, trying to learn something about it, right, in the problem. Well, if I have an x minus 1 in the middle, what I need is a plus 2 to get to x plus 1. So I'll add 2 on each side, and I'll get that for this specific case where delta is equal to 1, and therefore x minus 1 is less than that amount, x plus 1 at its very largest, and x plus 1 at the largest amount that x plus 1 can take is going to be 3. Right? So the maximum of x plus 1, right, is 3. Then you might say, great, okay, that's a couple of confusing inequalities. What does that allow us to do? Well, if we take this information and think about it on this line, it lets us write another inequality. When we talk about something being at its maximum, well, we know that the absolute value of x minus 1 times the absolute value of x plus 1 will always be less than or equal to the absolute value of x minus 1 times the maximum value of absolute value of x plus 1, which in this case is 3. Okay, so we create this new inequality chain. So we're moving from left to right. What we knew before is actually we're stating to be less than or equal to the absolute value of x minus 1 times 3. Right? Now we have a numerical expression that's less than epsilon. So we're going to pull this amount, right, and say, well, if the absolute value of x minus 1 times 3 is less than epsilon, then the absolute value of x minus 1 should be less than epsilon over 3. Okay. So this is a second way for us to think about what delta would need to be. We could also choose delta to be equal to epsilon over 3. But we should immediately, because epsilon can take any value, right, whether it could be 0.01 or 1,000, recognize that sometimes delta being equal to epsilon over 3 will make delta larger than 1. And we don't want that to be the case. So in fact, our actual choice for delta, and this is where it's a little strange to think about it this way, but our actual choice from delta is the minimum of two numbers. Epsilon over 3, and this is normally the choice, or 1. Okay, so we either choose the minimum of those two numbers, whichever one is smaller. And chances are the epsilon over 3, this is going to be the smaller one, especially when we're in the spot where we're making proofs. Okay, because we want this to be very, very small. All right, so that's a lot of analysis. Now we're actually into the proof itself. And the proof here is not going to be particularly difficult now. So the proof starts with what we know. X minus 1 has got to be less than delta. Choose the minimum of the two. Well, if we want really small values, we're going to choose epsilon over 3 to be the value. Well, then I'm going to multiply 3 over. So I get 3 times absolute value of x minus 1 is less than epsilon. Now I could distribute that 3 on the inside of the absolute value, but that's not going to lead us back. Maybe go all the way back to the top. That's not going to lead us back to showing that initial line here. That's the line we want to show. Instead, we can add an additional inequality. We know that 3 times the absolute value of x minus 1 will be greater than or equal to x minus 1 times the absolute value of x plus 1. That's that work that we did before. It's very small. Remember that oftentimes in the proof, we're just going backwards, right, to what we started with. Well, let's get rid of that middle part, right? Because what we really care about was what's on the far left and what's on the far right. We've been using that idea of the maximum value of x plus 1 being 3 in order to relate the two of them together, because we need a numerical bridge and not an expression. Well, I can, using the reverse of our property from before, I can get x squared minus 1 is less than epsilon, and then I can get that to x squared minus 3 plus 4 is less than epsilon. And that is what we wanted to prove. And that's the end of the proof.